Hi, welcome to the 6th trigonometric tutorial. Today's tutorial is titled the Advanced Trigonometry Graph. It is a fairly tricky section of trigonometry, so I do need you to pay careful attention. Also, you need to be very familiar with the first 5 sections on trigonometry. I'd also recommend you go through some of the sections under functions before attempting this tutorial. Reference to this is made in the DVD workbook. Let us begin by attempting a few basic graphs. I want you to have a go at the following. Press pause on your DVD player, and when you return we'll go through it together. The first one we're looking at is sine of 2x. Now I've already drawn the sine of x graph, as you will see it drawn in your workbook. On top of this graph, I'm now going to draw the graph of sine 2x. Now sine of 2x means that at every x value we're going to double it before looking for the sine of that. For example, instead of sine of 90, we're going to say sine of 2 times 90 when x is 90. By the way, this is the x-axis, this is the y-axis. At 90, it's going to be sine of 180. Now sine of 180, looking at our standard sine graph, sine of 180 is equal to 0. Sine of 0 times 2 is 0. 180, 2 times 180 is 360, sine of 360 is 0. 2 times 270 is 540, sine of 540 is 0. Sine of 720 is 0. Sine of negative 180 is 0, 0, 0 and 0. There's a slight problem with this graph. It's only 0. Yeah? No. Think about this angle 45 degrees. 45 times 2 is 90. That means that at 45 we're looking for sine of 2 times 45, or sine of 90, which is equal to 1. At this point here, which is 135 degrees, it's going to be negative 1. So do you see the pattern that's starting to form? Basically what's going to happen is that our graph is now doubled. So our sine graph now in the positive, think about this, in the positive 360 degrees, there's supposed to be one wave. But sine of 2x now means that there's 2 waves. First wave ending there, second wave ending there. So we've doubled the graph. The next graph we're going to look at is y is equal to 2 sine of x. 2 sine of x, now think about this. Sine of 90, when x is equal to 90 degrees, sine of 90 is supposed to be 1. 2 times 1 is equal to 2. Sine of 180 is 0. 2 times 0 is 0. Sine of 270 is negative 1. 2 times negative 1 is negative 2. And 0 again. So what's really happened with saying 2 times sine of x, all we've done is we've doubled both the amplitudes and the troughs of our wave, but our graph still looks pretty much like the sine graph. It's just each amplitude and trough has been doubled. The next graph we're going to be looking at is y is equal to sine of x plus 30 degrees. Now you will remember from the functions tutorial that x plus 30 degrees means that we are moving our graph to the left 30 degrees. Think about this. When x is equal to negative 30 degrees, that is going to be negative 30 plus 30, which is 0. Sine of 0 is 0. When x is equal to 60 degrees, that's going to be sine of 60 plus 30, which is sine of 90. 180 degrees is going to be moved up as well. 150 degrees plus 30 is 180. Sine of 180 is 0. So do you notice that every point on this graph has moved 30 degrees to the left? That should be over there, but we are going to end it there. That's where it peaks, 30 degrees. Well, actually over there. And the whole graph has just moved 30 degrees to the left. That's sine of x plus 30 degrees. And just carry on up there till 360 from negative 360, because that's our limits, or rather that's our range. X is an element of negative 360 up until positive 360 degrees. I've got the cos of x graph drawn. On top of it, we're going to start with the first graph. Y is equal to cos of a half x. Now cos of a half of x is going to be the opposite of doubling the graph. You will remember sine of 2x meant that we had two waves in place of the one. Cos of a half of x means that we're now going to have half of this graph. When x is equal to 0, 0 times a half is 0, cos of 0 is 1. When x is equal to 90, that's going to be a half times 90, which is 45, which means that it's going to fall somewhere over here. When x is equal to 180 degrees, it's going to be cos of a half of 180, or cos of 90, which is 0. Sorry, when x is 270, it's going to be cos of a half of 270, which is cos of 135 degrees, which means that that point is going to fall somewhere over there. And when x is equal to 360 degrees, it's going to be cos of a half of 360, which is the same as cos of 180, which is negative 1. The same thing will happen in the negative axis. Basically what's going to happen is that our graph is now going to look something like this. It's going to drop down at 0 at 180 and negative 1 at 360. Notice how different these two graphs are. The standard cos graph versus this graph. It looks very odd. The only reason it looks so odd is because I've limited myself to x having a range of negative 360 degrees all the way up to positive 360 degrees. If it went on further than that, it would still take on the shape, except the x values would be different. That wouldn't be 90, that would be 180, that would be 360, that would be 540, that would be 720. The next graph we're going to be looking at reads y is equal to a half cos of x. Now you will remember that the sine graph we dealt with was y is equal to 2 sine of x, which doubled. Now we're looking at a half of cos of x. 0 degrees, cos of 0 is equal to 1. A half times 1 is a half. Cos of 90 degrees is 0. 0 times a half is 0. Cos of 180 degrees is negative 1. Negative 1 times a half is negative a half. 0, positive a half. And in the negative axis, it's still going to go 0, negative a half, 0, positive a half. That means that this graph is going to look a bit like this. Notice that all we've done is we've sort of halved the amplitude and halved the trough in our wave to get the graph y is equal to a half cos of x. The final graph we're looking at is the graph y is equal to cos of x minus 30 degrees. X minus 30 degrees means that we're taking our graph and we're shifting it to the right 30 degrees. So instead of the peak being at 0 degrees, it's now going to be at 30 degrees. Instead of it dropping at 90, it's going to drop at 120. Instead of it being a trough or negative 1 at 180, it's going to be that at 210. That is going to be at 300 degrees, and it's going to peak at 390, but we're not going to go till there. We are going to go from there though. And so our graph is going to be our normal cos graph, except it's been shifted 30 degrees to the right. So it's going to peak over there, and it's going to turn and start coming back down already. And that is the graph cos of x minus 30 degrees. We are now going to look at the tan of x graph. We are only going to look at one transformation, tan of x minus 45 degrees. Now all that this means is that our tan graph is going to be moving 45 degrees to the right. That means that each of our asymptotes as well will move 45 degrees to the right, and each graph will follow those asymptotes, will also move 45 degrees to the right. So it will still be the standard tan graph, except now it will be moved 45 degrees to the right. I did take a bit of a lazy way out in an untidy way, but that's the graph tan of x minus 45 degrees. You can also do transformations with the tan graph, for example tan of 2x or tan of x, but because this graph stretches to infinity in both the positive and the negative y-axis directions, it won't really change the shape of the graph. It might just pull it a little bit tighter in or loosen up a bit, but essentially we're still going to be looking at the same tan of x graph. I hope that you found those basic sketches quite easy. We are now going to look at sketching multiple graphs on the same set of axes. I want you to have a go at the following. Press pause on your DVD player, and when you return, we'll go through it together. We are now going to look at the graphs of y is equal to sine of 2x and y is equal to cos of x minus 30 degrees drawn on the same set of axes. I'm going to start off with my set of axes. I'm going to cheat, which I don't want you to do. I want you to draw it properly in your workbook. Well, you can't cheat like I can. And I'm going to take my graph, sine of 2x, and I'm just going to put this on my axis. The next graph I'm going to draw on is the graph that I did earlier of y is equal to x, y is equal to cos of x minus 30 degrees, which will go over there. I'll just rewrite that. And the blue graph is the graph y is equal to cos of x minus 30 degrees. Except the blue graph, we've now called it g of x, or the cos graph rather, and the sine graph, we've called it f of x. We are now going to look for the points of intersection, or rather the points where these two graphs meet. And I'm going to draw that in black. There's 1 point over there, 2 points, 3, 4, 5, 6. Now my graph is highly inaccurate. Both my graphs are fairly inaccurate. If you draw it properly, you will find that there are 2 points of intersection over there, because you're going to find the red graph goes slightly above the blue graph, or the sine graph goes slightly above the blue graph. That means that there are 1, 2, 3, 4, 5, 6, 7, 8 points of intersection between these two graphs. We are now going to look at how to calculate those points of intersection. Draw this graph in your workbook. I trust that you found that quite easy. Now in your workbook, you will notice that right under the space that I left for you to sketch the graphs, there is a section titled Interpretation. We are now going to look at that, how to interpret of a trigonometric graph. I want you to have a go at the interpretations that are set out in the workbook. I want you to have a go at the interpretations that are asked in the workbook. Press pause on your DVD player, and when you return, we'll go through it together. We are now going to look at our graph, and we are going to find the points of intersection. Unfortunately, it's very difficult to do that accurately by inspection. We are going to have to do that by calculation. Now look at your graph carefully. Wouldn't the points of intersection be when f of x is equal to g of x? That means now f of x we know is the sine graph sine of 2x. G of x is the graph cos of x minus 30 degrees. When f of x is equal to g of x, to get our corresponding x values, we need to solve this mathematically. What's the problem with this? One is a sine and one is cos. As you saw in the previous exercise, it was an easy one to solve. Keep this as sine of 2x is equal to sine of 90 degrees minus x minus 30 degrees. We can now drop the signs on one condition. We use general solution. So there's two possible solutions. The one is 2x is equal to 90 degrees minus x minus 30 degrees, and this is in quadrant 1 plus k times 360, where k is an element of integers. This will now read 2x is equal to 90 minus times a minus is plus 30, which is 120 degrees, minus x, but that minus x can be taken over to make that positive 3x, 2x plus x. 3x is equal to 120 degrees plus k times 360 degrees, where k is an element of integers. That means that x is equal, to get x on its own we divide by 3. What we do to one side we do to the other side. That will be 40 degrees plus k times 360 divided by 3 is 120 degrees. This is only one solution. This is our quadrant 1 solution. Where else does sine operate as positive? In quadrant 2. That means that 2x is equal to 180 degrees minus 90 degrees minus x minus 30. This will mean that 2x is equal to 180 minus 90, minus times a minus is going to give us positive 30 degrees. 180 minus, so that's minus times the positive 30 degrees is going to give us negative 30 degrees. So essentially it's 180 degrees minus 90 degrees minus 30 degrees. 180 minus 90 is going to give me 90. 90 minus 30 is going to give me 60 degrees. Minus x times a minus is going to give me positive x plus k times 360, again where k is an element of integers. Take the x across, that will be 2x minus x, which is just x, is equal to 60 degrees plus k times 360 degrees, where k is an element of integers. Here are our two possible solutions. Now, remember I said we need to find our points of intersection. Keep these two solutions written down. I'm going to bring back on my graphs. Huh? I don't need that. Alright, we'll just have to cut out that little bit in between. I'm now going to be looking at my graphs. On this, let us put our two solutions. Our one solution was x is equal to 40 degrees plus k times 120 degrees, where k is an element of integers. Our other solution was x is equal to 60 degrees plus k times 360, again where k is an element of integers. Now let's try and find our points of intersection. When k in this first solution, I just want to erase this piece over here. In our first solution, when k is equal to 0, that's going to be x is equal to 40 degrees plus 0 times 120, which is just 40 degrees. That means that that solution is 40 degrees. When k is equal to 0 here, this solution is going to be 60 degrees plus 0, which is 60 degrees. When k is equal to 1, this is going to be 1 times 120 degrees, which is 120, plus 40, which is 160. When k here is equal to 1, that's going to be 360 degrees plus 60 degrees, which is beyond 360 degrees, so we are not looking for that solution. When k here is equal to 2, that's going to be 40 degrees plus 2 times 120 or plus 240. 240 plus 40 is 280 degrees. That's in the positive axis. Now let's look at the negative axis. The next k value we're going to use is -1. When k is equal to -1 over here, 40 minus 1, okay, I've got that already, -80 degrees. When k is equal to -1 over here, that's going to be 60 degrees minus 360 degrees, which is going to be -300 degrees. When k is equal to -2, that's going to be -240 degrees. 40 degrees minus 240 degrees is going to give me -200 degrees. And those are all of my points of intersection. Please note that I'm missing another point over there. When k is equal to -2, that's -200 degrees. When k is equal to -2 over here, that's going to go beyond -360, so we're not worried about that one. But look here, when k is equal to -3, that's going to be -360 degrees. 40 degrees minus 360 degrees is going to give me the point -320 degrees. Now please note that these 8 points of intersection are only the x values. I have only given you the x values or the angles. If you want to, and in some cases you are required to, find the total coordinates of each of the points of intersection, I'm going to give you an example on the 40 degrees. The x value is 40 degrees. To get the y value, we're going to have to say sine of 2 times 40 degrees, which is the same as sine of 80 degrees. On a calculator, sine of 80 is going to yield an answer of 0.98. 0.98 rounded off to 2 decimal places. You can do that for all of the angles. I did not bother to do that myself. And that's if they ask you to calculate the coordinates of the points of intersection. I only asked you to calculate the x values or the angles where the graphs intersect. We are now going to look at interpreting this information. I'm going to take this off because we no longer need it. The first thing I asked you for was, when is f of x greater than or equal to g of x, or rather for which values of x is f of x greater than or equal to g of x. Now think about that. F of x is the graph sine 2x. G of x is the graph cos of x minus 30 degrees. Basically, I'm asking for which angles, or rather for which x values, is the red graph higher than the blue graph. It's going to be higher than the blue graph over there, even though it doesn't look like it. So that's from -320 degrees all the way up until -300 degrees. And then from there to there, again, the red graph is above the blue graph. So that's from -200 degrees, x is greater than or equal to, but less than or equal to -80 degrees. Less than or equal to we're using, and greater than and equal to, because we're asking when is f of x greater than or equal to g of x. Thereafter, from 40 degrees up till 60 degrees. Thereafter, from 160 degrees all the way up to 280 degrees. And that's the four sort of series of results where f of x is greater than or equal to g of x. The next bit I asked you was, when is f of x less than or equal to g of x? Less than or equal to g of x means that when is the red graph falling below the blue graph? When is f of x falling below g of x? That's going to start at negative 360 degrees and it's going to end at negative 320 degrees. It's then going to be from negative 300 degrees all the way up to negative 200 degrees. Then from negative 80 all the way up to 40. Then from positive 160 all the way up to 280 degrees. And those are the sets of points where f of x is less than or equal to g of x. Sorry, it's not the 160 to 280, my bad. It's from the 60 to 160 where f of x is below g of x. So it's from 60 degrees to 160 degrees, and then from 280 degrees all the way up to 360 degrees. The last thing I asked you for was, when is f of x increasing at the same time g of x is decreasing? Now let's look at this. G of x is the blue graph. The blue graph is decreasing from there all the way until there. At which point between that is f of x increasing? F of x is increasing from there all the way up to there. That means that the x values we're going to be looking at are negative 225 degrees. That's from there all the way up to that point over there, which is negative 150 degrees. So x is greater than or equal to negative 225 up until negative 150 degrees. Where else is g of x decreasing? From there till there. In that point, where is f of x increasing? Funny enough, from there till its peak, which is a very short interval. Increasing, decreasing, and then increasing again. Let's look at that first bit. It's from the point that g of x starts to decrease, which is at 30 degrees. Because that's where its peak is. All the way up until this f of x peak, which is going to be at 45 degrees, which is over there. Where else? Well, f of x starts to increase from there, but g of x is decreasing up until there. So it's from that point till that point. That point is f of x's lowest point, which is at positive 135. So x is greater than or equal to 135 degrees, but less than or equal to that point over there, which is equal to 210 degrees. How do I know 210? Because the lowest point of the g of x graph should be at 180, except it's been moved 30 degrees to the right, so it's 180 plus 30, which is 210 degrees. Are there any other points where f of x is decreasing while increasing while g of x is decreasing? No, there aren't. We are now going to add a slightly higher level of complexity, in that we are going to start using the general solution as well in our graph interpretation. I want you to have a go at the following first before we go through it together. Press pause on your DVD player, and when you return, we'll work through it. The example I gave you to do read, draw the graphs of f of x, which is equal to sine of x minus 45 degrees, and g of x, which is equal to, I'm going to draw that one in red, g of x is equal to cos of 3x. I'm going to start by looking at the sine of x minus 45 degrees, which means that my graph sine of x has moved 45 degrees to my right hand side. So instead of it peaking, instead of it being 0 at x is equal to 0, it's going to be 0 at x is equal to 45 degrees. Instead of it peaking at x is equal to 90 degrees, it's going to peak at x is equal to 135 degrees. And then instead of it coming down back to 0 at 180 degrees, it's going to come back down to 0 at 225 degrees, which is somewhere over here. Now we are stopping at 180 because I did give you the range from negative 180 degrees all the way up to 180, but we'll sort it out now. Then instead of x going to negative 1 at negative 90, it's going to drop to negative 1 at negative 45 degrees. And instead of x going back, or instead of sine of that going back to 0 at negative 180 degrees, it's going to go back down to 0 at negative 135 degrees. And the next one, instead of it peaking at negative 270 degrees, it's going to peak at negative 225 degrees, which is somewhere over there. That means that this graph is going to look like that, but we're only starting at the 180 degree mark. Whoops. That's going to go down till there. It's going to be at its lowest point there. It's then going to increase all the way up till there. Then it's going to start dropping, and it's going to stop at 180 degrees. And the same over here at negative 180. So that's the standard sine of x graph, which has just been shifted to the right 45 degrees. That point is 45 degrees. And that point over there is negative 135 degrees. We can calculate this intercept if we want to. In fact, I think we're going to do that. That's when x is equal to 0. So that's not sine of 0 any longer. That's going to be sine of 0 minus 45 degrees, which is going to give us negative root 2 over 2. And that's that intercept over there. And that's the graph f of x. The next graph, g of x, is going to look at the standard cos graph, except it's 3 times as big, or rather 3 times compressed. So it's cos of 3 of x. When x is equal to 0, cos of 0 is 1, so that point is fine. When x is equal to 30 degrees, 30 times 3 is 90, cos of 90 is 0. When x is equal to 60 degrees, it's going to be cos of 180, which is negative 1. And then 0 again, and then all the way up to 1, and then 0, and then negative 1 over there. And the same thing in the negative quadrant, 0, negative 1, 0, positive 1, 0, negative 1. That means that our graph is going to look a lot like this. And that's the graph g of x. It's the standard cos graph, but it's 3 times 3 sort of waves instead of just one wave. In the next question, I ask you what are the points, or what are the x values where the two graphs intersect, or rather when f of x is equal to g of x. Notice that there's 1, 2, 3, 4, 5, 6 different points. We are now going to find those different x values. To find those x values, we're going to say it's when f of x is equal to g of x. That means that sine of x minus 45 degrees is equal to cos of 3x. Problem: sine and cos are different functions. I'm going to make the sine x minus 45 degrees is equal to sine of 90 degrees minus 3x. Now I can drop my signs. X minus 45 degrees is equal to 90 degrees minus 3x plus k times 360, and this is for quadrant 1. Or I could say that sine of, oh sorry, not sine, x minus 45 degrees is equal to 180 degrees minus 90 minus 3x plus k times 360. Both of these are when k is an element of integers. And this is for quadrant 2. Remember that sine is positive in quadrant 1 and quadrant 2. Because we're using general solution, we've got to use quadrant 1 solution and quadrant 2 solution. The quadrant 1 solution is going to read x minus 45 degrees is equal to 90 minus 3x. Take the minus 3x across, it becomes 3x plus x, which is 4x, is equal to 90 degrees plus 45 degrees, which is equal to 135 degrees, plus k times 360, which means that x is equal to 135 degrees divided by 4. 136 degrees divided by 4 is going to give us, that means that x is going to equal 33.75 degrees, which is 135 divided by 4, plus k times 90 degrees. That's our one possible solution. Our other possible solution is going to be x minus 45 degrees is equal to that. 180 minus 90 is going to give me 90 degrees. Take the 45 across, so that becomes plus 45 degrees. Minus times a minus 3x becomes positive 3x. Taken across becomes negative 3x. X minus 3x is going to give me minus 2x is equal to 90 plus 45 degrees plus k times 360 degrees. 90 plus 45 is equal to 135 degrees. That means that x is equal to negative 135 degrees divided by 2, which is equal to negative 67.5 degrees plus k times 360. All of this happens when k is an element of integers. That means that these are our two possible solutions. Taking that onto our graph, which we have over here, the two possible solutions we have are either x is equal to 33.75 degrees plus k times 360, or x is equal to negative 67.5 degrees, also not plus k times 360, plus k times 90 degrees. And our other solution is negative 67.5 degrees plus k times 180 degrees. Now there's one mistake I made in the previous example. When I divided through by this negative 2, the 360 has to also be divided by the negative 2, which will make it 180 degrees. So it's plus k times 180 degrees. The reason it does not have to turn into a negative k times 180 is because, remember, k is an element of integers. Because k is an element of integers, k can be positive or negative in any case. So we don't have to change that to minus k times 180. Now let's look at our possible solutions. The first one being when k is equal to 0. That's going to be 33.75 degrees plus 0, which is just 33.75 degrees. When k is equal to 0 here, x is going to equal negative 67.5 degrees. Now that's negative 30, negative 60. That means that this point over here is negative 67.5 degrees. When k is equal to 1, that's going to be 33.75 degrees plus 90 degrees, which is going to give me 123.75 degrees. 123.75 degrees is going to come over here, 123.75 degrees. Because remember that this is the point 120. So we haven't yet found the solution for that. We are going to. When k is equal to 1 over here, this is going to be negative 67.5 degrees plus 180 degrees, or 180 degrees minus 67.5 degrees. It will be the same thing, which is going to equal 112.5 degrees. When k is equal to negative 1, this is going to be 33.75 degrees minus 90. 33.75 degrees minus 90 degrees is equal to negative 56.25 degrees. So that is the point negative 56.25 degrees. That's when k is equal to negative 1 over there. When k is equal to negative 1 over here, this is going to be negative 67.5 degrees minus 180 degrees, which is going to take us past negative 180, so we are not interested in that. When k over here is equal to negative 2, that's going to be 33.75 degrees minus 2 times 90, or minus 180, which is going to give me negative 146 degrees 0.25, negative 146.25 degrees. And those are all our possible solutions for the range, or rather for the range. X is an element of negative 180 degrees up to x is equal to positive 180 degrees. The next question asked, when is f of x greater than g of x? Now f of x is the blue graph. When is the blue graph above the red graph? Starting from our left, we can see that it's from negative 180 degrees. I'm going to do this in red. So when is f of x greater than g of x? Remember, this time it's now greater than, not greater than or equal to. That means that it's from negative 180 degrees. X is greater than or equal to negative 180 degrees, but less than negative 146.25 degrees, or from negative 67.5 degrees. X is greater than up until the point negative 56.25 degrees, or x is greater than 33.75 degrees but less than 112.5 degrees. So that's from 33.75 degrees, x is greater than that but less than 112.5 degrees. And our last instance, I'm just going to erase this. Make sure that you've copied all of this down, by the way. The other point is going to be over there. From x is greater than 123.75 degrees but less than or equal to 180 degrees. Now it can equal to 180 degrees because it can be that point. The graph f of x is greater than g of x at 180 degrees. The reason it can't be equal to 123.75 degrees or any of these other points is because that is where the two graphs are exactly equal to each other. The next question I asked was, when is f of x and g of x decreasing at the same time, for which x values? Well, let's start by looking at the f of x graph. We know that the f of x graph is decreasing from there right up until there. That's when the f of x graph is decreasing. In that space, where is the g of x graph decreasing? The g of x graph is decreasing from there till there. So when both of these graphs are decreasing, lies between the points x is equal to negative 120 degrees all the way up until x is equal to negative 60 degrees. From there to there, both graphs are decreasing. It cannot equal to negative 60 or negative 120 degrees The reason it can't equal those 2 points is because that's where the graph is 0 and not necessarily decreasing or increasing. Where else is f of x decreasing? F of x is decreasing from that point till that point. Is g of x also decreasing on that interval? Yes, it is. So it will be from that point all the way up until that point. That peak occurs at 135 degrees. So x is greater than 135 degrees but less than 180 degrees. The reason it's not less than or equal to 180 degrees is because that's the turning point of g of x. So at 180 degrees, f of x is still decreasing, but g of x is starting to turn. That means that for the last option, when f of x and g of x are both decreasing, there's only 2 possible solutions. And that brings us to the end of this fairly tricky tutorial. Make sure that you understand everything we have done today. It is a fairly complex section and usually counts a lot of marks. Go through the exercise that I left for you in the workbook before progressing on to the next tutorial titled 2D and 3D triangles.